Hello, my name is Rocio and welcome to my Physics 2212 Lab 3 Magnetic Field of a Bar Magnet. Today I'll walk you through the introduction to the lab and fundamentals for it, our observational model, computational model, a comparison of the two, and further understanding. In this lab, we are to measure the magnetic field of our small bar magnet and look at its distance dependence. We'll apply our knowledge from the PHYS law, use a magnetometer app and GlowScript to find the magnetic field and compare our models. The fundamentals for this lab and formulas will be the PHYS law for calculating the magnetic field of a magnetic dipole, which we'll manipulate by taking the natural log of it, and then we'll also need the distance dependence equation for a bar magnet. Okay, so for this lab, our system is only going to be the bar magnet, and we're going to assume that we have correctly and precisely lined up our smartphone with the North Pole. And so before we actually start the process, we'll position our phone to align with the north, and that will help us determine how the perpendicular is the east-west axis, and that's where we'll place our bar magnet. And from there, we'll determine where our magnetometer was in our phone because it differs for every phone. And in our results, we found that our n is equal to negative 2.70, well, about negative 2.8. And then our natural log k is equal to negative 14.1. Our k is 7.45 e to the negative 7. Our r is equal to 1 meter. And we're going to apply our PHYS law to find that the magnetic moment of the bar magnet is 3.73 amperes per meter squared. In our observational model, we found that the distance dependence equation was y equals negative 2.7983x minus 14.109, and we did this through first finding our magnetometer on our phone, and then from there placing a bar magnet perpendicular to our north, so running through the east-west axis, and from there we slid our phone horizontally and vertically as well in order to find the strongest magnetic field emission, where it was coming out strongest from. And from there we found the on-axis distance of our magnetometer by using the averages of several values, and that's what you can see in the graph of the Excel chart, and that's where we found our formula. So we input our physical constants into the computational model and made a representation of the bar magnet as a cylinder, and we put in our magnetic moment of the bar magnet in there, as well as define the function for a magnetic field at any point. Then we defined our observational axes and then made two on-axis observation points with arrows to demonstrate the magnitude and direction of the bar magnet's magnetic field. The same was done, but this time 4 perpendicular arrows for the magnitude and direction of the bar magnet's magnetic field. Now, using our perpendicular distance from our experiment, we input that and we were able to find the 45 degrees off-axis magnetic field arrow, and then we calculated the magnetic field for that with the same function. These are our results for the computational model, and this is an image kind of showing what it would look like or what it should look like. In our observational or experimental off-axis field, it would have been 2.98 e negative 4 teslas, whereas our computational off-axis field was 3.53 e negative 4 teslas, and that made the difference 16.9%. And keep in mind that our computational model had less errors than our experimental one. Further understanding, the purpose for orienting our experiments to compensate for the magnetic north and laying it out at a specific location was so that the Earth's magnetic field wouldn't have interfered and made our difference a lot greater than 16%. And if we were to stick two identical magnets together end to end and run the experiment again, we would have probably doubled our magnetic field because there are now two magnetic fields to account for. However, the direction would have been the same because they're placed end to end, so we don't have to worry about repulsion.